Okay, I've given everyone a minutes to show up, but why don't we just get going? Most of the first few slides are introductory stuff anyway. And so I'm going to talk about predictive maintenance. If you are trying to get into a different session, why don't you just stay and hear about predictive maintenance anyway? Hopefully it will be interesting to you. My name is Sarah Ewing. I am a lead data scientist, and I am from Boise. This is me and my daughter out at Siemens Gulch while we were hiking a few months back. So to start off with, what is predictive maintenance? It's predicting when something needs maintenance before it breaks and affects the normal workflow. And how do we go about doing that? And so what you have to do is, I'm sorry, my PowerPoint is misbehaving. Can I please have a sec? Okay, here we go. So predictive maintenance is when predictive maintenance is when you try to replace preventative maintenance. Preventative maintenance is going out every single day and checking the same exact thing to make sure it hasn't broken. So for example, we have Bob. He's a mechanic, and he goes out every single day and checks the serpentine belt on an engine. The idea is that we would put an algorithm in place on that engine that would say that the serpentine belt is going to break sometime this week, and Bob needs to go out and replace it when everyone is not using that engine in the factory. A lot of questions come up during that process, like what is the normal workflow? What are the types of failure that occur on that engine? Is the serpentine belt one of the main ways that the engine breaks? How is maintenance recorded? And what type of feeds do we have coming off that engine? If we don't have any sort of regular numeric measurements, then it isn't really helpful to start doing predictive maintenance. You need to gather some of that data before you go in. But the idea is to reduce the amount of time that a maintenance worker needs to spend on all the parts and to have everything fixed during the natural downtime. So when the plant is down or when the engine is not being used. In order to do predictive maintenance, data is very important. You need a team of individuals that are skilled at this. And then we're going to go through some use cases based on these pieces of information, specifically looking at nuclear power plants, roller coasters, and HPCs, or high performance compute units. So what type of data do you need to do predictive maintenance? There are a lot of different types of signals that we can get off of just an engine. You have binary data. Is the engine being used? Yes or no? And then the duty cycles, what type of signals are being sent to the engine to go forward, go backward, to stay put. That is a binary signal, surprisingly. There's analog data, like how many rotations is that serpentine belt going through? Vibration monitor, how much is that engine shaking? You can do infrared thermal scans, which are actually really helpful with looking at different components and the likelihood of failure. And then every time Bob goes out and checks the serpentine engine and he writes, or checks the engine and writes that the serpentine belt is not going to break, that's an open text. So we have to convert that into a standard text, and that's a piece of data that we need during this process. And an actual video feed of the engine is helpful, surprisingly. And this is not a complete list. There are more ways to gather information off of an engine. But the really important part is that a lot of this information is that it's part of a whole giant plant, and it isn't just one engine. There are hundreds or thousands of engines in a plant, and each engine might have multiple feeds coming off of it, and each feed is at every millisecond or every second. And so the amount of data you end up getting is really overwhelming. And so a lot of the time you have to have a data engineer come in. Data engineering, when you are doing predictive maintenance, is key. Data engineering is when you take those raw files that are coming off of those sensors or those video feeds and you actually put it into a database in some sort of structured way or unstructured way. So that way a data scientist or an analyst can get at it and manipulate it and make it more meaningful. A lot of the time, because we have such a giant feed of milliseconds coming in, the signals don't change every millisecond, but it pings you to let you know, hey, I'm still off. Hey, I'm still off. And that's recorded every millisecond, which is really overwhelming as a data scientist. And so the data engineer ends up reducing that down to maybe only records where the engine has turned on and has turned off, and we don't need to see everything that occurs in between it. That's called a status change. But there are other things that can be done, such as frequency tables. How often does something change in an hour or in every couple minutes? Latency, so when you have multiple sensors and they talk to one another, when a sensor says, hey, you need to turn on, and the other sensor actually can be recorded in the amount of time it takes to send that signal and react and turn on. There's clustering, so groups of sensors for that engine should behave in a similar way. And then there's chatter. So a lot of these sensors have noise or have meaningless information that occur on them. And we have to filter through that to something that's actually meaningful. And what we reduce that down to is something called a chatter. And so some of the sensors, as we would say, are very chattery. So they would talk, but not actually do anything, if that makes any sense at all. And then we have the maintenance data. So Bob actually writing serpentine belt actually broke. And what you end up doing is taking all these feeds off of the engine and corresponding it to that open text of, hey, the serpentine belt broke, and measuring what was occurring before the serpentine belt broke, so we can have an alarm that says next time before the belt breaks that it's going to break, and you have X amount of hours to react to that belt breaking. And so that's why we have the sensors or that feed information as your input or your X variable, and your maintenance data as your output or your Y variable. And all of that is something that data engineering helps with, those feature engineering type tasks. So what does this actually look like in a flow chart? So the part that I was talking about with the data engineering and the status change table, that is the blue section of this chart. So you get the feed off the sensors, you make a status change table, and you feature engineer it into something like chatter, pattern, or latency, which are the common algorithms that have cute little names that we use. But the event data is something in that yellow box that you can see on your screen that's right in the middle. The event data is really hard to work with because sometimes it's open text, sometimes it's standard text, and it's not always clear what it means. And so reducing that large feed of information down to a ground truth, like Bob writes, hey, serpentine belt looks like it's going to break today, when he checked it this morning, and then later that day, false alarm, belt didn't break. But if you have an algorithm go through and read the first statement, it looks like standard belt breaking, and then the next statement is it didn't break. But how do you translate that consistently in a way that is the ground truth? So it's a very difficult task to do. The blue and the yellow go into the green box. And that is when we do a lot of that machine learning magic, that data science magic. And so we dev out the different models. It isn't just one or two algorithms, but you try out a lot in that space. You see what works best. You end up iterating a lot with the subject matter experts and try to define the type of alarms that they want to see. Some places want alarms on things if it's even a slight likelihood that something's going to break. And some places only want alarms where we are 100% sure this is going to break within the next 24 hours, and we will alarm on that. And those are very different standards to live by, and you almost always have to iterate with the customer about what they want to see on their end. And then the final step is to make those alarms pretty, because what I receive as an alarm and what maintenance engineer would receive as an alarm, it needs to be very clear hey, this sensor at this location at this time, it's probably going to, would be what I would see. And then the maintenance engineer would actually see, hey, this is probably going to break within the next X amount of time. You need to fix it this evening when everyone goes home in between shift changes. And so we have to iterate through that as well. So that is the orange box. So to do this whole process, it's not just a rogue data scientist wandering around looking at data and just, you know, fitting those beautiful algorithms in. You have to have a data scientist, typically more than one, that work through these problems because they're usually gigantic problems, a whole factory, a whole roller coaster, a whole power plant, a whole room of servers, if you will. And then you have data engineers that build out things like your database and the different tables and changing that data from raw into tables that the data scientist can access. You have people that have worked in these plants for years and actually going and interviewing them and talking to them and talking to the maintenance people helps as a data scientist, because my models are basically going to be what the maintenance engineer feels in their gut. And I'm just going to try to create it into some really useful rules using machine learning. There are visualization experts so that when the subject matter expert or the maintenance individual sees these alarms, they know what they mean. And the line of business user, which is, you know, kind of who you're responsible to at that factory, the managers and stuff like that. And that is your team. So those are the group layer on the very top. What you can see in this chart is that it's lots of different steps and it's all of that team working together to produce this. So you have the data being put into the cloud or being put into servers, so on cloud or on-prem. You have that database layer, the Greenplum, the Hadoop, the Spark, the GCP big table, if you will, and the data processing and making that feed real time. And then using different tools and services. And then finally, the data scientist, the analytical layer that makes everything go, if you will. So it's a group effort. It's not just a lead data scientist running in and throwing out algorithms. Okay, so now you know about the data and you know about the individuals that have to work together to put it together. But how? And where would you want to do predictive maintenance? Well, one of the first places that I got to do predictive maintenance, or preventative maintenance, if you will, was on nuclear power plants. So if you didn't know how nuclear power plants work, they're a little bit different than other power. So when coal or fossil fuels are used, they can be brought up really quickly and down really quickly. And then when solar and wind are used, you collect solar whenever the sun's out. So in the middle of the night, you're not collecting solar. And if there's no wind, that turbine's not going to turn on that wind farm. But nuclear is different because it's usually the base loader for an electrical grid, meaning that it's a constant. It's not something you can bring up and take down really quickly. So it's the base load. When a nuclear power plant's up, it's up for an extended period of time. When it goes down, they take it down I think almost every year, and they usually take it down for a couple months at a time. When it's down, there's a ton of maintenance that's performed, and often the maintenance time, that month or 2-month period, ends up getting extended to 3 months and so on to deal with different parts of these aging nuclear power plants. And so it's really important that maintenance is done really well. And so what we did was trending. And not just like trending on Twitter. We looked for trends in maintenance. So as more frequently maintenance was done on different sections of a plant, that would indicate that that whole system would be needed to be replaced sooner. And so it was a lot of generalized linear models with compound distribution. So you have your gamma Poisson and your beta binomial is what was commonly used. I do want to be clear that everything in a nuclear power plant typically has a backup system, and that backup system almost always has a backup system. So there is usually 2 backups to every single system. And it's important that a lot of the time what happens in a nuclear power plant is the human element fails out. And a lot of the human factors individuals that I worked with really didn't like the fact that I would crack jokes that a human built the plant, therefore anything that fails in the plant was a human failure. But you do have mechanical failures sometimes. There are some really cool things that happen in plants, or, well, I guess some people might not think they're cool, but when you read reports and you have to collate all this data, there are snake and vine attacks on nuclear power plants. So a lot of plants gather their fresh water for their cooling systems from rivers and lakes. And in those freshwater systems, sometimes they get clogged with vines, which is pretty normal and it's very seasonal and they have a way to deal with that. But that does get recorded as maintenance and there's really not much to do about it. One thing that did happen that was very odd is there were so many snakes that jumped into the river due to the hot weather that it actually clogged one of the water filtration systems at one point. And we have termed that a snake attack, which is just fun to say and not fun to think about too hard. And so the next use case I'm going to talk through is roller coasters. So a lot of preventative maintenance is gone into having you and I have fun for a couple minutes going really fast in these vehicles on these steel rails. Maintenance is regularly performed daily, weekly, monthly, and bigger things are done every 6 months. I want to stress that each roller coaster is unique. So if there is a roller coaster in Orlando and a roller coaster in Orange County, California, and they are the same exact track with the same exact mechanisms and built on the same exact day, those coasters are absolutely different due to weather and many other factors, such as the individuals performing maintenance and other things that are very difficult to capture. So the algorithms for those two very similar but different roller coasters are unique. And so the reason we want to perform predictive maintenance instead of preventative maintenance is that way the coasters can run longer and customers' satisfaction is not affected, as well as the fact that won't you feel safer if you go on a roller coaster if there is some sort of algorithm or some sort of AI along with that preventative maintenance that is going on. And so a lot of it was communicating with those, again, maintenance engineers. There was a gentleman actually who would go out on the roller coaster with a large stick, and he worked on this roller coaster for over 30 years, and he would place the stick on different parts of the roller coaster and put it on the temple of his head so he could feel the vibrations, and he could tell you if something was going to break in that section of the coaster. But the great thing is we have these things called vibration monitors, and they work almost exactly the same, and it isn't going around with a stick checking different parts of the coaster. But talking with the engineers allowed us to get that insight. So what a lot of the time is done is the PLC, the programmable logic control, is tapped, and we'll get millisecond feeds of data coming off of these coasters. Each coaster has thousands of these sensors put on it, and it's just overwhelming the amount of data you can get from a roller coaster, and it's very cool. And so in order to identify abnormal behavior, we would try to identify it 3 months before it occurred so it could be fit into those maintenance schedules of weekly and monthly and 6 monthly. What we ended up using was modified ARIMA models, hyperparameterization, goodness of fit, and even those black box things called neural nets to get these results. A lot of the maintenance data was Bob writing emails, if you will, to his manager, and they weren't always very helpful. Sometimes I'm using Bob as this fictitious mechanical engineer, but he would write emails to his manager and say, hey, that there was a bag of goldfish left on the roller coaster. The cracker, not the fish. And that wasn't always very helpful because it wouldn't let me know what part of the roller coaster that occurred on and what part I should see a spike in the feed on those sensors. And other things very similar to that, like recording the leaf type. instead because a leaf fell in front of one of the sensors rather than what sensor they removed the leaf from. And so trying to get them to change their culture around it was really helpful and produced a lot of really good results. So one thing I might have mentioned previously was a duty cycle. Duty cycles are binary signals that are sent on roller coasters and other mechanical vehicles to say, hey, go forward, go backward, and stop. What we're specifically looking at on this graph is a go signal being sent. And this is just 2 milliseconds of data, just to give you an idea. And the first signal, the first upward rectangle that you see here, is cut off. So it's actually a noise signal and has no meaning. But the last 3 rectangles, it's a very clear signal being sent of go on that vehicle to go to the next section. And so trying to look at this with the low brakes and the high noise, you can see that the red section on that graph going up and down corresponds to the table in the upper part of your screen. So you can really clearly see what this 2 milliseconds of data looks like. And so each part of the coaster has different signals being sent at different times. But this is just one sensor that we're looking at, and this is many different rows. And the actuality of the amount of data being sent during this period was every single millisecond was a 1 or a 0 in addition to the actual changes occurring. So the amount of information that was sent to the data engineer to distill it down to this so I could have a look at it was an awful lot of work. So that go signal, if we just look at the high go signal, so if we look at this frequency right here, so the high go, and we just want to look at how many of these signals are being sent within an hour. We can see that typically for a high go signal on this specific sensor, sensor ABCD, we normally see 300 to 400 signals being sent to, hey, go to the next section of track vehicle. And you can clearly see when the ride is down. You can also see when maintenance is occurring on this attraction, and it actually cut into normal access to the ride. And so we can see here's some normal behavior. But as you remember in the GIF I just previously showed you, that there were other signals being sent, such as the logo, the brakes, and also the other mechanisms I was talking about. So pausing and also going backwards. And so when we break it down to all of these different signals that can be seen on one sensor for a binary signal, we have all of these 12 different feeds occurring. And so how do we do an outlier identification? So what is abnormal here? This is kind of trending upward. We can see that there are some crazy spikes, but what truly is weird about this one single sensor for one part of the track? There are consistent spikes, and they're seen across many different sensors, or excuse me, many different signals. And so 1, 2, 3 spikes on 3 different signals, that's pretty odd. These spikes over here could be seen as odd, but you don't have so many odd occurrences occurring at the same time. And so one way that we do multivariate outlier identification is this thing called neural nets. And they're a lot of fun to work with. Sometimes people use the buzzword of deep learning, but the original purpose of an autoencoder neural net is to compress pictures. So when you're in Photoshop and you take a big image and you make it smaller, that's a neural net autoencoder that's doing it. But that's also really great for identifying really weird things. And so just for example, a lot of the time autoencoders can be trained to do other things other than compressing images. So for this example, there's an original 3D image of a mushroom, and using an autoencoder for the encode and decode, we can create a learned representation of that that is 2D that only has 4 colors. And so the very important thing about an autoencoder is if you're using it for outlier identification, do not use it on raw data. So everything that you see over here was feature engineered. The data engineer and I worked really closely together to do this. Okay, so the next use case that we're going to talk through is high performance compute clusters, or HPCs. So the thing about HPCs is that most of the time right now, preventative maintenance is not performed. Nuclear power plants and roller coasters, someone goes out and checks things regularly. In HPCs, no one does that. Software is updated intermittently, and everyone just reacts to downtimes. That's why a lot of different places offer maintenance as a service, and there are IT guys on call. Hey, the server's down, I can't log in. And that person wakes up at 2 a.m. and fixes that server. And so a lot of the times it's really hard to do this because there are monitoring systems with different logging tools that create different types of data. The software updates, changes the types of data that are provided. And of course, anyone who's ever used a computer or tried to go out and had Gmail be down, Gmail does go down sometimes. It's really frustrating and makes you go, well, why am I using Gmail? Well, it has a superior spam filter, but that's beside the point. So what do system logs look like? They look something like this, but servers oftentimes have a lot of different data feeds, and there are more than the ones listed here. So you have system logs, failed job reports, PBS server, Nagios, SEC logs, SEC events, hardware failures. There's just a lot. And so it ends up looking something like this. You have a time, you have where the process occurred, and then you have the message associated with it. And what we want to do is scrape information out of all of that and make it more meaningful, because a lot of this doesn't help. Same messages over and over. It doesn't say where errors are occurring. Let's just reduce this down to something that's meaningful. So we look for metrics, so actual numeric values, and then also vector embedding. So it's kind of like changing words into numbers. And when we do that, using those two pieces of information, there are a multitude of analytical things that we can do to make it meaningful and produce that alarm that says, hey, HPC or this job is going to fail. And we do ARIMA models, naive Bayes classifiers, random forests, autoencoders, neural nets. And a lot of this is very NLP strong, natural language processing strong. So what do you do in this environment when you have HPCs? It's not just a bunch of sensors coming off of a roller coaster. You have several hundreds or even thousands of computers all working even on the same job. Some calculations take days and hundreds of computers to compute. They're a lot more magnificent than some of my models, but that's beside the point. So what do you do to train your model? So you have to use a subset of the data. You can't use all of the compute's system logs for all 8 different data sources for the thousands of sources across all time. That is just overwhelming. So you try to take a subset of that data. So you try to stick it to 1 month or a couple months, and you only look at some randomly selected compute nodes. And so we ended up using a test train split that was balanced, meaning that the amount of failure it looked at and the amount of success it looked at was equal. This is important to note because the amount of times the server fails is probably about 1%, but that 1% is really important and we want to catch it. But that amount of information is pretty small. And so we try to balance those models, if you will, with failure and success. And so one thing that we really noticed is that the language in failure logs is dramatically different than the language in success logs. How do I know that? Because using the same 10 words in the black graph, if you look at the red graph, which is our failures, and the green graph, which is our successes, you can dramatically see that there is a frequency difference between the red and the green. And so we can see that this type of messaging differs between compute nodes and success. And so we can achieve accuracy in predicting whether or not a job is going to fail based on the type of language that is in the syslog. And we don't even need a lot of words. We only need about 10 or so. And so the idea is that an algorithm will go through and read the log lines and can decide if the log came from a job that is or is not going to fail within a certain amount of log lines. So give the algorithm 100 log lines and it says we're 80% certain this is going to fail. We are 10% certain this isn't going to fail or is going to fail. So anyway, what we're just trying to do is predict the likelihood of failure. And another thing to note is that hardware failures and software failures are dramatically different. And what we ended up running into is that a lot of the metrics approach isn't naturally, innately something you could do. So there's not a lot of numeric values that you can pull out of these logs. There are, however, a lot of words, and those words end up being very informative when we go to say whether or not something's going to fail. The good thing is that metrics can be added in. So someone has to go in and tell those feeds, hey, report the temperature, report the CPU usage, report all these different metrics. Okay, so Sarah, you said words. How do you predict failure? So for 2 different jobs, one that is going to fail and one that is going to succeed. So this is our failure, and this is going to succeed. Not the word failure. We can't tell you what word, but a single word was used across one job. One job uses multiple compute nodes, and we can see over time of the job spiking of this negative word in those compute nodes in the system log. Whereas in this job that succeeded, those words weren't really present. And so if we drill down, we can, at just the word level, the vector embedding, if you will, we can identify what job is and isn't going to fail before it gets to the point of failure. And then we can shut it down gracefully. And looking at a handful of words, we can have the probability of failure. So what we have over here is the probability of failure. And this is a job that I believe took about 2 days to perform. And here's another job that also took 2 days to perform. But this one succeeded and this one failed. The failure job ends up hitting 100% likelihood of failure multiple times in the job just based off a handful of words that we could see. And the same handful of words was used in the success job, and we had a max less than 80% likelihood of failure. Probably because a lot of CPU usage was occurring, and that's usually a driver for failure in these jobs. So I know that was, I tried to be very brief and go through 3 different use cases, but if anyone has any questions about any of the use cases, please feel free to throw them into the chat or unmute yourself and ask away. I don't think I can hear you either. But I can see the chat. So if anyone has any questions, feel free to put them in the chat and I'll be more than happy to talk. Thanks, guys. So the interesting thing is that retraining models occurs most frequently in roller coasters, and retraining occurs probably about once a month due to we ran into maintenance individuals not recording maintenance, and so models need to be retrained to recalibrate to that maintenance, and then extreme weather changes, whether it be rainy or not, and so that ended up greatly impacting the models. Maintaining a model in production is, I think, really difficult, and so I would have it send me reports once a week, and then we would actually report our accuracy of our models once a month to the executive team at our client. And so it was really fun to do, and going through that whole process of creating those reports and then actually having those reports auto-generate and then email them to me so I don't have to rerun code. It was fun to figure out how to do that. At least for a data scientist, it's usually quite out of our wheelhouse. So a lot of model selection is trying out things in the space. Autoencoders for outlier detection wasn't a really big use case of autoencoders when I first started applying it, but we were trying that against even PCA, I think the MSE, we were trying it against many different methods, just standardizing the open text of Bob saying, hey, serpentine belt's gonna break, or I replaced it today. Standardizing that text and then trying out all the models is a lot of metadata recording. So, you know, you do your test train split, and then you record the accuracy on your training data and on your test data. And then you say the method that you tried, and then you tweak that method a little bit with a little bit of feature engineering. You record how you tweaked it, and then you report those accuracy again. And if you're really good, you do test, train, and validation with your data, where the validation is only, data set is only looked at when you get it down to 1 or 2 models. That way you aren't biased in your model selection. And when you have as much data as you have in predictive maintenance, you definitely do that test, train, and validate split. Does that help? Okay, good. So I think they have the end of this section scheduled to end in 5 minutes. So just a warning, if you have any questions, get them in now. So it is, oh, I do this so often. It is, my brain's just going event accuracy and alarm accuracy, but it is, I can't remember the name. You use the values in an F1 calculation, but if you will, that is alarm accuracy and event accuracy, meaning you can have the alarm go off 5 times for 1 imminent failure, and you can have them go off before the alarm, and that is an alarm accuracy. And if it goes off 5 times before and it gives someone enough time to react, then those alarms are good. And then event accuracy is how many events do you actually flag as, because if you go off 5 times for 1 event and then you go off 0 times for another event, that's 50% accuracy, but your alarm could be 100% accurate because it only went off those 5 times. And so trying to balance with the customer what they want to see on their side. Do they want an alarm to go off every time before an event, or do they only want highly accurate alarms? And that is a conversation, and I usually iterate very closely with the customers. I don't just go out and force it to be an F1. F1 is a way that you calibrate the alarm accuracy and event accuracy, balancing for both, where it's just like a silly little calculation of measurement, if you will. And there's also the idea of false negative and false positive. That is what you have in your confusion matrix. So if you have an alarm go off and there was no event, and it's just trying to deal with that confusion matrix, it gets a little confusing because you have alarms and event accuracy, and so each one can potentially have a confusion matrix. So using live documents being like a Google spreadsheet. And so you can put in the methods that you're trying. You can have different individuals assigned to certain methods to try out all the different ways you can put a random forest, or all the different ways you can put an ARIMA model on something, and then my responsibility is to try all the ways that you can do an autoencoder and then record all the accuracy. And while it sounds really straightforward, you just throw on an autoencoder. Are you going to use vector embedding or not use vector embedding? How are you going to shape your autoencoder? Because there's a lot of different ways you can shape something and it can still be called an autoencoder. What type of activation are you going to use on your neural net? And so it gets really big. But if you assign a method to an individual and they try everything that they can possibly think of with that method to produce results, and then you are all recording that in a live Excel or a Google Doc, because they have it now that you can all work simultaneously on one document. Really nice. It works really well. Yes, I have used GitHub. I hope I've used GitHub for not for tracking for analytical methods that you've tried, but for just version controlling around a code. You have, a dev environment and a production environment, if you're lucky, and you dev stuff out, you try out all the models in development, and then the really good model that you all agree on gets pushed into production. And hopefully you don't have to ever roll back, right? My opinion for state of the art was honestly on roller coasters. No cost was high enough to try out a new method, whether it was just the different locations you could tap a sensor to pull out its data. So you can tap it actually on the roller coaster, you can tap it back in the hub, so at the PLC, and the feeds that you get on that are very different. The sensitivity of the sensors and just getting into all that hardware, and then actually eventually putting a Raspberry Pi out at the sensor to house the model. And if an alarm was going to go off for that, it would go off in that Raspberry Pi and immediately go to the control room. And that is edge computing, and that is really exciting and fun to do. So that would be the most state of the art, not unfortunately HPC. I don't know if they're gonna kick us out because the session's supposed to be over at 11:15. But I'm willing to answer more questions if you want. Well, a lot of the time we didn't have to wait on data science. The biggest problem was always getting data to load into our production environment. And that took longer than deving out the models. But to be practical, I would say narrowing it down to a type of model, 2 to 3 weeks. It also depends, a lot of the time is setting up your environment. So architecting your stack, what sort of database, what sort of operating system, what sort of tools are you going to give your data scientist access to, and then the data engineering, that takes up a lot. But when you actually get down to it and then the data's cleaned and it's in a table and the data science has access to it, I would probably say 2 to 3 weeks to get it down to a model that'll work well. Usually data scientists like to fiddle and make stuff perfect. So if you give them the opportunity, they will keep messing and trying out different things for a month or two. And usually those findings that they have through the course of a month or two are really good and useful. And so it ends up making the model better. And a lot of the time for the data scientist, unless you force them to go on to the next thing, they'll keep fiddling and trying to make that model better. It's somewhat of an addiction. So how long between when I figure out the model and when it actually goes into production for the client? So if we're this model works great, let's put it out into the environment. Oh, to retrain a new version of the model? Retraining usually is pretty fast. I would say you usually train it on the most recent amount of data. That windowing size is dependent on each customer and the amount that thing changes. It depends on the environment. So roller coasters are once a month. HPCs are, they don't change dramatically much. And nuclear power plants also don't change dramatically much. And so annually was kind of what we did for nuclear power plants, monthly for roller coasters, and HPCs might be something that I'm still working on, so I don't have an absolute answer for you yet. But between the amount of time it takes from like, hey, this is a perfect model, and hey, let's put this out into the environment, I would say that that leap is, you know, in a perfect world, it would be 2 weeks, but reality is probably a full month to iron out all the bugs, get it into the GitHub repo, and make sure nothing's going to cause you to set back. All right, guys, I'm not seeing a new question. So, and we are 3 minutes past. Yeah, standardizing open text is really difficult, and it's a lot of fuzzy string logic, if you will, to get it to something that's meaningful. And you have to train the fuzzy strings. So reading someone's awful text, like Lee software experience, different logs, that syntax of all of the words being glomped together, and then actually saying it should look like this, and then training a model to understand what these things should look like. We can continue talking about this. This is what I do. So I do enjoy talking about it. And if you want to ping me on LinkedIn, you're more than happy to do so. Also, I run the Boise Data Science Meetup. So if you want to ask me predictive maintenance questions or other data science questions, you can come to the Boise Data Science Meetup, and we meet once a quarter. And we are more than happy to keep chatting about data science until the cows come home. I think last time we had presentations, and then we stayed on for about 3 hours talking about data science after our presentations and everything. And when it's not COVID, we commonly meet over at BSU and then walk across the street, and I'll get a beer on Tuesday nights once a quarter. So it's a really fun group. I highly recommend them. And just type in Boise Data Science Meetup, and it's usually the first response on your Google search. All right, guys. Since we are over, I'm going to end this. I hope you all enjoyed this and you might have learned something about predictive maintenance.